Physics students, good afternoon. Mr. Fugit here. In our video today, we'll be looking at a few problems on test number 6. Specifically, the problems that we will look at will cover over the concepts of momentum that we've been learning about in class. So here, in this video, we'll specifically be looking at problems 6 and 7 on the review for test number 6. You will notice the problems will not be located on the board. If you would like a copy of the problems, they're located on Canvas along with a key to those problems. So I'll go ahead and read problem number 6 and then we will get started. In an out-of-control ceramics workshop, two clay balls collide and stick together. The first ball has a mass of 3.42 kilograms and collides with the second that is initially at rest. I'm going to go ahead and write that down. We've got here in problem 6, two objects that are going to collide. Let's call this the mass of object 1, which is 3.42 kilograms. And the initial velocity of object 1, which we don't know. And then we've got this other ball with a mass that we don't know, but an initial velocity of object 2 initially, which is 0 meters per second. So, kind of know one thing about each object. Object 1 is moving to the right with some velocity, and object 2, we don't know the mass, is at rest. We're told the first ball collides with the second. The resulting two-ball system, meaning the objects are going to collide and stick together, moves with a speed equal to 1/2 the original speed of the 3.42 kilogram ball. What is the mass of the second ball? So we want to find the mass of this object, and we're told the objects collide and stick together, and they move with half the speed of, or half the original speed of the first ball. So we've got a lot of things going on here. Let's start by taking these ideas of mass and velocity to find momentum. So initially, what would our initial total momentum be? So we've got mass of object 1 multiplied by its velocity, plus mass of object 2 multiplied by its initial velocity. But here, I'm going to go ahead and cross out the momentum of object 2 because we're told it's not moving, so it doesn't have any momentum. So from there, the momentum of object 1 would just be its mass, 3.42 kilograms, multiplied by the initial velocity of object 1. Don't really know what that velocity is, but this is really all I can do. Now I'm going to put a box around this equation so that if I come back to it here in a moment, I have it there. Now after the collision, here's what we're told. The objects are going to move together, so something like this, let's assume they're going to the right. Sorry, I dropped something over here. And because it's likely the total momentum is also going to be to the right because the initial momentum is to the right. So after the collision occurs, here's how we would represent the momentum. The momentum final would be the mass of both objects together, because we're told it's a two-ball system after the collision. Mass of object 1 plus mass of object 2 multiplied by the total final velocity. Since the objects are moving together, we can assume their velocity would be the same. Now we are told one thing. The the speed of the objects after the collision is equal to 1/2 the original speed of ball number 1. So here's what that means. The final velocity of the objects together is equal to 1/2 the initial velocity of object 1. So now I'm going to rewrite the momentum equation this way. Final momentum is equal to the combined mass, m1 plus m2, multiplied by, rather than Vf, but as 1/2 V1 initial. Because now I have a final momentum equation and an initial momentum equation that have the same velocity variable in them. And maybe we can then use that to cancel some things out. So here, looking at our problem statement, it doesn't look like we're told anything about significant external forces, which means we can set our initial momentum equal to our final momentum. So let's do that. The momentum initially will set equal to the momentum finally. The momentum before the collision equals the momentum after. So before the collision, our momentum was expressed this way. 3.42 kilograms multiplied by the initial velocity of ball 1. And our final momentum was equal to, as we saw just a moment ago, the mass of both objects, m1 plus m2, multiplied by 1/2 the initial velocity of a ball 1. So here's what I know here. I have a term v1i and v1i on both sides of our momentum equations. So technically what I could do here, excuse me, is divide both sides of my equation by v1i. That term, v1i, is multiplied on both sides of my equation, so I can divide it out. So I'll now rewrite what I have left. 3.42 kilograms is equal to m1 plus m2 multiplied by 1/2. Right, we just divided out the v1i term. Now, I need to get rid of the 1/2 so that I can find what m2 is. So I'll multiply this side of the equation by 2, which means I've got to multiply this side of the equation by 2. Right? Whatever I do to one side, I've got to mirror on the other side. So 2 multiplied by 3.42 would give me 6.84. That's equal to 1/2 times 2. Those will cancel out. So then I've got m1 plus m2. Now, we're already told what m1 is. We know m1 is 3.42 kilograms. So here we go. 6.84 kilograms is equal to 3.42 kilograms plus m2. So now to get m2 by itself, I can just subtract 3.42, subtract 3.42, and I end up getting, well, a mass of object 2 that is the same as the mass of object 1. Now, here's why that value fits our scenario. Think about the total momentum before our collision. 3.42, the mass of one object, multiplied by its velocity. Now, after the collision, we're told the mass is going up, which means if the total momentums are the same, an increased mass would probably have to have a decreased velocity so that the momentums are equivalent. We're told that the velocity goes down by a factor of 2. It's cut in half, which means it's likely that our mass has to go up by the same factor, 2. So really, in order for our momentum to be conserved, our velocity is going down by a factor of 2, and the mass is going up by a factor of 2. We half the velocity and double the mass, so that the total momentum here is conserved. So, here, the fact that our mass is the same as object 1 really just fits with the scenario. The velocity goes down by a factor of 2, the mass goes up by a factor of 2 in total. So here, hopefully this gets us going on problem number 6, looking at the values of the two objects before and after the collision. Okay? As well, if you have any other questions, you are welcome to direct them to me, as well as check Canvas for other resources. We're now going to move on to question 7. Question 7 says this: 2 students collide in a hallway. Student A, with a given mass, is moving east with a velocity of 3.45 meters per second. So we're just going to draw this out. We've got student A, who's moving east, and we're told that student A has a mass of 60 kilograms. And he's moving east, so the initial velocity of student A is 3.45 meters per second. And then we've got student B, who's running west with a velocity of 5.8 meters per second. Student B is running west. We're told student B has a mass of 50 kilograms, given to us in the problem. And the initial velocity of student B is 5.8. I'll refer to that as a negative 5.8 because velocity is a vector and we need to factor in the direction here. So here we're told after the collision, student A hits B and then recoils to the left. And we're told that velocity. And we want to know the velocity of student B after the collision. So we know a lot of information about what's happening before the collision. And we're not really told anything about significant external forces here. So we can probably assume the momentum is conserved. So let's go and start by finding the initial momentum prior to the collision. So we'll need the mass of student A and student A's velocity to find student A's momentum, plus the mass of student B multiplied by student B's initial velocity. And thankfully, the problem gives us all of those numbers. So let's go ahead and plug those in. We've got student A. I might run out of space here, so I'm going to go ahead and drop the units off just to save some space. 60 and 3.45 plus student B, we've got 50 and negative 5.8. So we can now go through and solve for the total initial momentum. 60 and 3.45 gives us 207 kilogram meters per second. Plus, we've got 50 and negative 5.8, which gives us negative 290 kilogram meters per second. And then we would add those values together. So we've got 207 plus negative 290, which gives us negative 83. Now really what that value is telling us is that the total momentum is negative, which means it's to the left, and all that means is the objects here, in comparison, the object moving to the left, student B, has greater momentum than student A. So now we're told after the collision, this would be our initial momentum, after the collision, student A recoils to the left, and we want to know what's going on with student B after the collision. So I'll get a little picture here just so I can track my numbers again. This is after the collision, student A is going to recoil, which means go back the other direction. Mass is not going to change. We're not told anything about student A gaining mass or losing mass. But the velocity of student A after the collision, we're told is 2.5. But since he recoils, or she recoils, that would be negative because of the change in direction. And then we've got student B over here, and that's, we don't know exactly which way student B is going to travel. Could be right, could be left. We'll just say the mass of student B, we know is 50 kilograms. We're not told anything about that changing. And the velocity of student B final is, we don't know. Maybe to the right, probably, but we're kind of unsure here. So, again, as we mentioned earlier, we're not told anything about the objects experiencing a significant external force. So we can probably assume the momentum we start with is equal to the momentum we end with. So let's set up an equation for the final momentum and then maybe use this number to help us find what we're looking for. So momentum final here would be the momentum of object A, or student A, mass of A, velocity of A, plus the momentum of object B, mass of B, final velocity of object B. So let's now plug in what we know. We know the total momentum, both objects combined, would be negative 83 kilogram meters per second. Now on the right side, I'm going to drop the units off just so we have enough space. Mass of A is 60, A's velocity negative 2.5 because of its direction, plus mass of B, which is 50, multiplied by velocity of B, which we don't really know yet. So let's go and multiply 60 by negative 2.5. 2.5. We get negative 150. So we'll now rewrite this as negative 83 is equal to negative 150 plus 50 multiplied by the final velocity of student B. So we'll add 150 to both sides of our equation, because again, I want to get VBF by itself. So these will cancel. So we'll take negative 83 plus 150, which gives us 67. And that's going to be a positive number, which means it's likely student B is going in the positive direction or to the right, which would make sense given the context of our problem. So 50 multiplied by VBF. And now finally, we'll just divide by the mass of student B. So we'll go 67 divided by 50. That would give us about 1.34 meters per second. So here, now we have a value for the final velocity of student B, which if I check what I'm doing here, 1.34, 1.34, exactly what we're looking for. So here in our scenario, really this is kind of a full analysis applying momentum conservation. Looking at the momentums of our two objects, our two students, prior to the collision, assuming that there are no significant external forces, So a scenario in which we can apply momentum conservation, and then using the resulting velocity or final velocity of student A, we then use our momentum equation to find the final velocity of student B. So hopefully this gets us moving in the right direction on question 7, looking at momentum and momentum conservation. As always, you're welcome to direct questions to me if you have them, and don't forget to check Canvas for other resources. Good luck.